Welcome back to The Explainer. So check this out. Right now, the exact device you are watching this on, whether it's your phone, laptop, whatever, it's actually being held together and powered by an entirely invisible force. Crazy, right? Well, today, we're taking that invisible force, specifically subtopic 2.2 for all you TVET students out there, and turning it into something real. Something you can hold, control, and actually build with. If you're studying mechanical or electrical systems, you already know that invisible forces run the world. But today, we're translating abstract physics into practical applied engineering tools. We are talking all about mastering magnetism. Here's our roadmap for today's explainer. First, nature's force. Second, the rules of magnetism. Third, the electromagnet. Fourth, magnetic control. And finally, number 5, the modern world. Let's jump right in. Section 1. Nature's force, the invisible foundation. Okay, so at its very core, a magnetic field is simply a region in space where we can detect a magnetic force. Simple enough, right? But here is the secret sauce, the one thing you absolutely have to remember. This field is always, like literally without exception, caused by the movement of charged particles. It really doesn't matter if it's the natural spin of electrons inside a solid chunk of iron or the active flow of an electric current running through a copper wire. Moving charges equal magnetic fields. Boom. That is your absolute baseline. And honestly, nothing illustrates our definition quite as brilliantly or on such a massive scale as our own planet. Earth is literally a planetary scale magnet. How cool is that? And why? Well, deep down inside, there's this massive core generator made up of molten iron and nickel. As the Earth spins, all those molten metals flow around, creating these absolutely massive electrical currents. And those moving charges, they generate this incredible magnetic shield that spans way out into space. Basically, nature is running the exact same physics we're about to engineer. Section 2, the rules of magnetism, fundamental rules. Now, what's really fascinating here is just the sheer stubbornness of magnetic poles. Notice that you can never, ever isolate a pole. Like if you take a bar magnet and just snap it right in half, you don't magically get a separate north and south piece. Nope, you just get 2 smaller magnets, and each one has its own new north and south. They are completely inseparable. And then we've got the fundamental rules of interaction. Unlike poles, so a north and a south, they will always pull toward each other. But like poles, 2 norths or 2 souths, they will violently push apart. This rule is unyielding. All right, let's map out these invisible lines of magnetic flux. Notice the flow direction here. Magnetic flux always travels from the north-seeking pole to the south-seeking pole. But I want you to pay special attention to the ends. You see how incredibly tightly packed those lines are right near the poles? That is because concentration equals strength. Where those lines of force cluster up tightly, that's where the magnetic field is at its absolute strongest. And as they spread out, the influence weakens. So here's the million-dollar question. We understand the field, we know the rules, and we can clearly see how the flux works. But a plain old iron magnet just kind of sits there, right? It's always on. So how do we take this wild, uncontrollable natural force and actually engineer it to our advantage? How do we make it do the work for us? Section 3, the electromagnet, building the core. Well, we're going to build our solution in 3 very specific steps. First up, we start with a simple, single loop of wire. Next, we multiply that loop into a solenoid coil. And finally, we introduce an armature core. Let's see what happens when we mix these ingredients together. And here is the stunning visual payoff. A single loop of wire, it really only produces these weak dual fields. It's not doing much. But stack those loops into a continuous solenoid coil, that's step 2, and suddenly we create very distinct north and south poles. The real magic, though, happens in step 3. Wind that solenoid tightly around a solid iron armature core, and man, that iron highly concentrates the magnetic flux. We literally just manufactured an incredibly strong magnetic field out of nothing but wire, iron, and a little electricity. Section 4, magnetic control, total control. I want you to really lock this next thought in your head. Control is the ultimate engineering advantage. Seriously, in the world of systems, automation, and modern machinery, a force that you cannot toggle on and off, it's basically just a heavy paperweight. Let's put this into perspective. Compare the permanent iron magnet to the electromagnet we just built. The permanent magnet is totally locked. It's always on. Its strength is fixed. Its poles are fixed. But our electromagnet? We can instantly turn it on and off. We can make it stronger or weaker just by tweaking the electrical current. We can even reverse its poles entirely just by changing the direction of that current. we have achieved absolute total control. Okay, so how do we actually use that control in the real world? Let's break down a classic piece of tech, the electric bell. Here we've got our power supply and switch, we've got the electromagnet coil, the iron armature and striker, and, this is the absolute most crucial part, the adjustable contact and spring right down at the bottom. That little setup right there is a mechanical gate, and it's the secret to making this bell buzz repeatedly. Now, before we see the full cycle diagram, let's prime ourselves with the 4 sequential steps of what's known as a trembling armature. Step 1. The circuit is manually closed by the user. Step 2. Magnetization instantly occurs. Step 3. The physical strike happens, which actually simultaneously breaks the circuit. And Step 4. The spring forces everything to reset. Let's watch this entire cycle in action. It's brilliant. You press the button, supplying the power. Instantly, the electromagnet violently attracts that iron armature. The hammer flies over and strikes the bell, but look closely at those contact points. As the armature moves, it physically breaks the electrical circuit. The electricity stops dead, and the magnetism just dies. Then the spring forcefully yanks the armature back, which, guess what, closes the circuit all over again, and the whole cycle repeats. Strike, break, reset. Strike, break, reset. It's super fast, and it is the pure genius of magnetic control. Section 5. The modern world powering the future. And you know, these exact same principles, they scale up to practically everything in modern industry. Number 1, think about those massive heavy-lifting cranes in scrapyards. Number 2, solenoid valves that literally pull a plunger to let gas or water flow through massive commercial pipes. Number 3, relays that use tiny, safe electrical currents to trigger massive, high-voltage industrial circuits. And number 4, critical safety systems, where a sudden spike in current creates a magnetic field strong enough to physically snap a breaker open and prevent a building fire. And this brilliantly illustrates exactly where your TV skills actually apply out there in the real world. It all comes together perfectly in the modern built environment. When you look at this commercial building cross-section, you're not just seeing walls and windows anymore. You are seeing complex HVAC solenoid valves meticulously controlling temperatures. You're seeing access control systems using heavy-duty magnetic locks on the doors. You're seeing relay switches routing crucial power all the way from the basement up to the roof. Your mastery of electromagnetism is quite literally what allows technicians to secure, heat, cool, and control the massive structures that we all live and work in. Which brings us to our final thought for today. We started out with a fundamental, totally invisible force of nature. We mapped out its stubborn rules, and we engineered it into a perfectly controllable mechanical tool. You don't know exactly how moving electrons can actuate massive physical structures. So if mastering these invisible magnetic forces is the absolute foundation of modern automation, what limits will your engineering skills push next? That's all for today's explainer, guys. Get out into the workshop, stay curious, and I will see you next time.